In this video, we're going to talk about exponential and logarithmic functions. First, let's talk about what an exponential function is. An exponential function is a function of the form f of x is equal to a certain number times a base, and then it's raised to the exponent. So the exponent is always x, and then we could add another number. So what's important to realize is that with exponential functions, the exponent is where you'll always find the x. Now there are two types of exponential function that we're going to be using to model. The first one is when we have an exponential growth. And a growth is when we're seeing that the function is increasing, like we see in the first one. This growth is going to happen when we have a number as the base, which is bigger than 1. So the base being the number that has the exponent attached to it. And another situation that we're going to be looking at often is decay. And decay is when we have something that's decreasing. And for decay, either we can have a situation where our base is actually smaller than 1, between 0 and 1, or we could have a negative exponent. So having a negative exponent is also going to form something that has an exponential decay. So we have two situations for our functions in which we're going to see a decay as such. Another important thing to know about exponentials is that all exponentials have a horizontal asymptote. Now the horizontal asymptote, this is going to be a straight line, a horizontal line. And this line is always going to have the equation y is equal to a number. And this is the line in which our function is never going to be touching this line. So we can see these examples here. Our function in this situation, g of x is equal to 2x plus 3, is approaching the line y is equal to 3, but it's never touching it. And what you'll notice in all of these examples is that the value of this horizontal asymptote is always what we're adding the number to. So in this case, we're adding 3, therefore the equation is y is equal to 3. Here we're not adding anything, so y is equal to 0, and here we're subtracting 3, so y is equal to negative 3. So that's a little trick to help you remember for the horizontal asymptote. Okay, let's look at our first example for exponential functions. An anthropologist monitors a grasshopper plague, noticed that the area affected by the grasshoppers is given by this function, where n is the number of weeks after the initial observation. So I'm going to highlight the important information, where n is the number of weeks. Draw the graph of the affected area on your GDC. So as soon as we have a function, we need to put that into our calculator. So I'm going to put into my calculator my function where I have 1.15 raised to the power of x. I'm going to click enter, and I'm going to see what it is in my calculator. Now at this stage, my window is not clear enough. So what I can do is I can zoom out, which is our third option. Let's zoom out until we see something. So now we see our function a little bit clearer, but I'm interested in what's happening here. So I'm going to zoom out around this area. And I'm going to change my y maximum so that it's something a little bit bigger, because I noticed that I'm having times 1,000 here. So that means that this number is going to be a lot bigger than 1,000. So let me put something like 5,000 and see what's happening on my graph. Okay, now everything is centralized around the y-axis, so let's maybe restrict our window a little bit, and I'm going to restrict the x's. Maybe since we're looking at x is the number of weeks, well, I can't have negative number of weeks, so I'm going to write -1, and then number of weeks 600, that's many years, so maybe 200 weeks should be enough. Okay. Even 200 weeks seems to be a little bit too much, but at least now it's a more realistic domain because we're interested in what happens when x is bigger than 0. Okay, B, find the original affected area. The original affected area, this happens when our number of weeks is equal to 0. So in other words, we're looking for the y-intercept. How do we look for the y-intercept in our calculator? We can click on trace, and we're looking at what happens when x is equal to 0. So I type in 0, and I get that the y-intercept is 1,000. So 1,000 is the original affected area. C. Find the affected area after 5 weeks and after 10 weeks. So now we have a situation where n is equal to 5. So again, I can use trace, 5, enter. After 5 weeks, my population is going, and my area, sorry, is going to be 2011. And then for double I, what happens when n is equal to 10? Well, trace 10, enter. After 10 weeks, my population is 4,040. Let's round that to 46. Wonderful. Part D. Find the using your GC, find how long it will take for the affected area to reach 8,000 hectares. 8,000 hectares, this is the value of our area. So in other words, we're asking ourselves, when is 8,000 equal to our function? And we're looking for the value of n. So one way we can do this in the calculator is we can go and insert a new function. My new function being 8,000. And then I can look for the intersection point. So now we see that 8,000 is not on my window because my y maximum only goes to 5,000. So let's make the y maximum a little bit bigger. And now we're going to be able to see clearly the intersection point. So we're going to go second function, trace. Intersection is our fifth option. First curve is in fact the blue. Second curve is in fact the red, and then they ask you to guess a point, so you can move your cursor a little bit closer and click enter. And we get the intersection point is 14.9 if I round to 3 significant figures, and 8,000. So find how long it will take for the affected area to reach 8,000. It will happen in the 14th week, so it's going to take 15 weeks in order to reach 8,000. Example 2. Professor Vikram investigates the migration season of bullboard birds from their natural wetlands to a warmer climate. He found that during the migration season, their population P could be modeled by this function, where T is bigger than 0 because T is the number of days since they start their migration. Find the population of bullboard birds at the start of the migration and in the wetlands after 5 days. So now that we have an equation, we can put that into our calculators. One trick I'm going to tell you is that try not to erase the functions that you have previously, and instead go onto the equal sign and click on enter so you deselect those functions. This is going to help you in an exam because you can always go back and check your answers for previous questions by just clicking on the equal sign instead of having to type the full equation again. So I'm going to put in the equation that I have, and I of course encourage you to do the same thing. 1.25 to the power of negative x. So negative x, this tells me that it's going to be a decreasing or a decay function. If I graph it, yep, in fact, it seems to be a decaying function here. I'm seeing that my y maximum seems to be a lot too big, and my x is probably a little bit too big. So I'm going to go ahead and restrict my window. Let's restrict that to 100, and my y maximum, let's bring that down maybe to 2,000 to have a better window. Okay, this is more appropriate. Find the population of bullboard birds at the start of the migration season. That means that our time is equal to 0. So trace x is equal to 0. This is going to happen after 1,750 days. Part double I, what happens after 5 days? Trace 5. This is going to be 1,481. There we go. Oh, and the first answer I said days, but we're talking about the population. So let me correct that. So it's not days, but we're talking about our population here. Okay. B, calculate the time taken for the population to decrease below 1,400. Okay, we're in a situation where we know the population and we're looking for time. So I can go and y is equal to, insert a new equation, and I'm going to look for the intersection point. Second function trace, intersection. First curve is the black curve, second curve is the pink. And then for guessing, I can just click enter because there's only one point of intersection. And we're going to get that this point of intersection is 9.32, rounded to 3 significant figures. Calculate the time it takes for the population to decrease below 1,400. So during the 9th week, this is going to happen. So therefore, it's going to take 10 weeks in order to be below our 14,000. So 10 weeks being our answer for part B. Part C. According to this model, find the smallest possible population of bulbul birds during the migration season. The smallest possible population, we're looking for our asymptote here. So there's a few ways that we can find our asymptote. We can use our table, and we can see what happens when x becomes very big for our exponential function. So if we click on second function graph, we're going to see our table. Now the black represents the exponential function. So as you increase x, you're noticing that everything seems to be approaching a certain number. Once this number stays constant, this means that your calculator is rounding the answer. So we are approaching this value of 1,350. That means that our asymptote is going to be y is equal to 1,350. This is a number that our population will never reach. It's approaching there, but it's never going to be equal to that. So an appropriate answer to this question is that the smallest possible population is going to be 1,351, because it's never going to go and be equal to 1,350, and it's never going to go under that. So our biggest population we could have is 1,351. Now let's talk about the logarithmic function. What's really important to know about exponential and logarithmetics is that they're inverses of each other. So this means that there's a perfect reflection from the logarithmic and the exponential function. So if we would have to graph this, remembering inverse functions are reflections across the line y is equal to x. If I have an exponential function, which looks something like this, right, where we have a horizontal asymptote, well, the reflection will be the logarithmic function, and it's going to look something like this. This is our log function, and this is our exponential function. And you'll notice that the logarithmic function, instead of having a horizontal asymptote, has a vertical asymptote. So that's the important thing to know about about logarithmic functions. They have a vertical asymptote, and a vertical asymptote is always going to have the equation y is equal to a number. And you see a couple of examples on the left here. So a couple of our logarithmic functions, you see they're going to have a vertical asymptote, and it's always x is equal to a certain number. In order to figure out what the vertical asymptote is, most of our logarithmic functions will have the format a times log, whatever base that is, x minus a certain value, and then maybe we're adding another value. And in order to find the vertical asymptote, you can look at the c value. So let me highlight this. This c value is going to help you determine what the asymptote is. For example, if we look at the function log base b of x, there's nothing added or subtracted. Therefore, the vertical asymptote is x is equal to 0. If you look at the other function here, where we have minus c, well, whatever that value of c is, That's going to be our horizontal asymptote. So if you want to remember this, our vertical asymptote is always going to be this value of c, remembering it's minus c. But if we don't need to remember this, because we're always going to be able to figure it out from our calculators. Example 1. The intensity level of sound L measured in decibels is a function of sound intensity S watts per square meter. The intensity level is given in the following formula. Okay, we have a formula. Let's put that into our calculators. So I'm going to go ahead and remove the previous examples. And I'm going to put my new function. I have 10 times log in base 10. Now log in base 10, this is our default log function, and this is the button where you just see log. This automatically is in base 10. If we had a different base, then what we would be using is clicking on math, and then we can scroll up because it's a shortcut, and you choose the button log base. And then this allows you to put whatever base you want as a logarithmetic. Then we have x times 10 to the power of 12. So I can have 10 to the power of 12, and that is my function. I can go ahead and graph it. This is not the best window, so let me try and do the standard window. Is this better for us? Not really. So let's zoom out and see what's happening. Okay, we see our function a little bit at the top. Part A. An orchestra has a sound intensity of this much watts per meter square. Calculate the intensity level. So we're trying to calculate the intensity level. The intensity level, that's L, and we know that the sound intensity is this. So identifying what we're looking for is the important thing here. If this is my value of S, this means this is going to be the X value that we're going to be putting into my function. So I can go ahead and trace, and my X value is going to be 6.4 times 10 to the power of negative 3. And I'm going to get my 6.4 times 10 to the power of negative 3. That is simply this decimal here. And my y value is 98.1 if you round to 3 significant figures. So what is the intensity level? The intensity level would be 98.1. Part B. A rock concert has an intensity level of 112 decibels. Now we know what L is, we know what our Y variable is, and we're looking for the sound intensity. So if we know what Y is, we can put that into our calculator as Y is equal to 112, and then we can find the intersection. Second function, trace, intersection, first curve, second curve, and then guessing the point, there's only one intersection point. So we get the value 0.158112. Therefore, the sound intensity is going to be 0.158, and that's in watts meters to the negative 2. Now, another type of example that we can do is examples where we're given some data and we're looking for the function, or we're looking for the model, right? And we're given some data. It's going to be the same way that we did for quadratics, for linear, and for cubic. Instead, we're going to be looking for either exponential or logarithmic. So the first thing we do is when we have data, every time we're going to put this into our lists. So we're going to have L1 and L2. Pause the video at this time and put in your data. Once you have your data, then the first part is plot these points into your GDC. So in order to plot these points, we need to turn on our stats plot. So we can go second function, y is equal to, and we want to turn plot 1, which is going to be list 1, list 2. We want to turn this on. We want to choose always the type scatter plot, and we're good to go. When we click on graph, we should see a variety of our plots and our y is equal to. I don't like to see what happened in my previous example, so I'm just going to go ahead and remove this from my graph because it's a little bit, there we go. I'm going to zoom in to see what's happening at these points. Zoom in, enter. Okay, so now we see our points here. Determine whether this is linear growth or exponential growth. Looking at my points, I'm thinking this looks more like an exponential since it's not a straight line. So for part B, we should be able to say that this is an exponential growth because we have a little bit of a curve happening here. And this is important for the IB. We're going to need to know what the functions look like in order to be able to determine what type of regression we want to do. Find a suitable equation. Since we said that this is exponential, we're going to go on to stats, calculate, and we're going to choose the exponential regression. Exponential regression is the 0 option, x and reg. This one, ln, this is the logarithmic regression, right? So we're going to have exponential regression. My x list was an L1, L2, nothing for frequency, and then we go ahead and calculate it. And now we're getting the function y is equal to 4.23 times our base 1.199, so that actually rounds to 2, and that is to the power of x. So this is going to be the exponential equation that best fits our graph. At this stage, I don't have an r² value that tells me how accurate this is. If this is your case in your calculator, that means that your stats diagnostic is off. So make sure you know how to turn it on. We go on to mode, and then you go down to stats diagnostic. Mine is off. Make sure you turn that on. And now you can repeat that calculation again. If I repeat my exponential regression, now I get an r² value. The r² value tells you if it's a good estimate of your curve. So 0.999, that's super close to 1. So that means it's a very good approximation of my curve. D. Hence, estimate the length after 10 weeks and state whether this is a reasonable estimate. After 10 weeks, that means we're replacing x by 10, and we're finding the length. So I can go y is equal to, and I can insert the function that I now have, 4.23 times 1.2 to the power of x. If I graph this, now I have my function, and I can go trace. I don't want to trace the plots, right? Because that's just going to give me the actual points. So I'm going to either you click up or down to change what you want to trace. I want to trace from the function, and then I'm going to write 10, and I get the point 10 and 26.2 if you round to 3 significant figures. So what is the length after 10 weeks? It should be 26.2. Now, is this reasonable? What we need to use in order to say if it's reasonable or not is your r² value. Since the r² value is equal to 0.99, this is very reasonable because it's a strong correlation.